Let's study about Hammond postulate. In this reaction profile, the red reaction has a higher activation energy, so that implies that the reaction is slower than the green reactions. Also, the intermediate-wise, the red reaction has a less stable intermediate than green reactions. In this case, the red reaction has higher activation energy, but intermediate is more stable, and green reaction has lower activation energy. That's why the reaction is faster, but intermediate is the less stable than red reactions. In the reactions, we postulate the transition state, but in most cases, transition state is difficult to capture or monitor. So that's why we need to use some kind of approximations to determine the structure of transition state. So here's two extreme cases. In this reaction, the reaction absorbed the energy and the product is less stable than the reactant. So this is an endothermic reaction. In this case, product is much more stable, so reactant is more unstable, and then the transition state is formed near to the reactant. So this is an exothermic reaction. So Hammond postulate says the transition state may be closer in terms of the geometric structure near to the energy state. So that means in the exothermic reactions, transition state may be similar to the shape or structure to reactant. In comparison, in endothermic reactions, transition state may have similar geometry to product rather than the reactant. So this is the Hammond postulate. In the addition reaction of alkene, usually we assume the carbocation as an intermediate. If the alkene is asymmetric, one side is di-substituted position and the other side is a free position, there are two possible carbocation intermediate. One is tertiary carbocation and the other is primary carbocation, and we know the tertiary carbocation is more stable than primary carbocation. So here, the stability of carbocation may affect the position of a transition state, and we can assume in tertiary carbocation forming the pathway, it may have lower energy state of transition state comparing to primary carbocation positions. In this case, if you think about the structure of transition state, this state, energy state, is closer to the intermediate comparing to reactant. Again, Hammond postulate says transition state may be similar structure to the energetically closer position. In this case, this transition state may be similar structure to carbocation intermediate structure. That's why if you look at this picture, so this is the starting material of alkene, and this is the intermediate of carbocation, then maybe the transition state. So you see here, double dagger, this is the transition state. Transition state is maybe similar to intermediate structure. So delta plus charge is introduced here, and partially this electron is moved to this carbon, and then that is donated to proton source, and then bromide is starting to leave from this complex. So this structure here, this transition state may be more similar to this intermediate rather than this alkene reactant. That is Hammond postulation. Now, if you look at this reaction, here double bond, alkene, and then HCl addition happens here. Then by looking at those structure, protonation happens here, and carbocation may be formed here, and then chloride should attack these positions. But interestingly, as the result of the reaction, we can observe the chloride addition not only here, it can be added to this position too. What happened? Now here, maybe intermediate is this secondary carbocation, and then this hydrogen is shifted from this position to another position. So this is a so-called hydride shift. Effectively, the result is interpreted as H- is moved to this position, and that's why carbocation was rearranged to this position. And the motivation is this secondary carbocation can move to more stabilized tertiary carbocation, and then this carbocation can be formed by equilibrium here. Then it generated the product. So this is the evidence of carbocation is really the intermediate of addition reaction in alkene. This type of rearrangement of a carbocation also can happen with methyl shift rather than hydrogen shift. So in this case, now this position is a tertiary, and protonation happens here. Then secondary carbocation is formed. Now there is no available hydrogen source to shift here. Then in this case, even methyl group is much bigger than hydrogen. It can be also shifted to this position, and it generates tertiary carbocation. And then the product is as a mixture of original position and methyl shift positions. So this may be a little more difficult case than hydrogen shift, but this is also observed as an example of carbocation rearrangement. So to summarize, to explain this observation, now the carbocation stability dominates those reaction direction. So tertiary carbocation is more stable, even overcoming the methyl shift the process, and then changing those secondary carbocation to tertiary carbocation, and then generate the product. Okay, this is the end of chapter 7. So next week we are going to move to alkene the reaction. So this week mainly we studied about the structure and property of alkene, and then the next week we seriously focus on the reactions of alkene. Okay, next class is next Tuesday, and assignment problem is already on the PLMS. Then as usual, the deadline for this the assignment is the Tuesday the morning. Okay, you may have some questions. Urgent one, you can send me Katok or email, or if not, you can ask the questions in the next class.